Welcome to the series of lecture on finite element analysis. In this part, we are going to solve a taper bar problem using finite element method. In the previous parts, we have derived the element characteristic equation for a bar problem. If we want to solve a bar problem using one-dimensional element, then we have to use this element characteristic equation directly. In today's session, we are going to use the same bar element to solve a taper bar problem. We will go to the problem. This is the tapered bar problem considered for today's class. For a tapered bar of uniform thickness T is equal to 10 mm as shown in figure, find the displacement at the nodes by forming into two element model. We have to use a finite element model with two elements. The bar has mass density of rho 7800 kg per meter cube. Young's modulus E 2 into 10 to the power 5 meganewton per meter square. So meganewton is 10 power 6. In addition to the self weight, the bar is subjected to a point load P which is equal to 1 kilonewton at its center. Also determine stress in each element and the reaction force at the support. Now this is the taper rod given in the question. So here in the top end is fixed end, bottom end is free, and the dimensions for this rod: top end 800 mm width, so thickness is 10 mm uniform thickness, so area of cross section at the top end will be 80 multiplied by 10. Similarly, when you take the bottom end 40 mm, actually this is 40 mm, so 40 mm multiplied by the thickness 10 mm, that will be the area of cross section at the bottom end. Then this distance from the fixed end to this point P where the load is acting, this is 150 mm, and the total length of the bar is 300 mm. So this is a mm. We are going to solve this taper bar problem by using one-dimensional line element. In case of line element, we are assuming it is a uniform cross-sectional member. So when we use the bar element, that is when we use the line element to solve the problem, we have taken the uniform cross-sectional bar. So the line element solves the problem exactly. But when you use this line element, one-dimensional line element to solve this tapered bar problem, which is of variable cross-section, then we have to convert this tapered bar into an equivalent bar to reduce the error in the solution. How to convert this tapered bar into a equivalent stepped bar, that we will see. Before making the finite element model for this tapered bar problem, first we are going to convert the given tapered bar into an equivalent stepped bar. Now here this is the tapered bar. The dimensions are in mm. Top end 80 mm, bottom end 40 mm width, then 150 mm from fixed end to point of application of the load, then remaining length is 150 mm. So now when you consider area of cross section at the fixed end as A1, so A1 is equal to 80 multiplied by 10 thickness, you will get 800 mm square. When you measure the area of cross section in the bottom free end, A2 is 40 into 10, 400 mm square. At the point of application, at this point, if you want to measure the area of cross section, then according to this given configuration, this point is exactly at the middle of this bar. So we can easily calculate the area of cross section at this point. This midpoint going to be considered as A3. Area of cross section at this point is A3. So A3 will be the average of A1 and A2. So A1 plus A2 by 2, which is equal to 600 mm square. Now in this problem, the point of application of the load is exactly at the middle of the tapered bar. Suppose if this point is not exactly at the center, right, then how to calculate this area of cross section? So for that, this formula is given. We can use this formula: area of cross section A of x at any point along this tapered bar, which is equal to A1 minus A2 multiplied by x by L. A1 is area cross section of the fixed end. A2 is area cross section of the free end. X is measured from the fixed end. We have to take X from the fixed end. Then this equation will give you area of cross section at any point along the tapered bar. Now, when you make this tapered bar into finite element model, in case of finite element, when we use the line element is of uniform cross section. So, when we select A1 as the cross section for the line element, then here I am showing that when you this first diagram will give, when we choose the area of cross section of the finite element is A1, then the model will be like this. Here I am showing this shaded region. This shaded region will be the error due to this finite element model. That is, this is called a discretization error. That means when we use a uniform cross sectional element for a variational cross section member, this type of discretization error should not be avoided. So, but what is the possible method to solve this problem? We can try to minimize this discretization error before solving the problem. Now, when we choose A1 as the cross section for this element, then this will be the discretization error. Similarly, when we choose A2, the minimum area of cross section as the area of cross section for this finite element, then also we will get this shaded region shows the error. This is called a discretization error. So, this error also maximum one. Now, to minimize this discretization error, what we are going to do is, we are going to consider two element model. Then for the first element, we are going to take the area of cross section for the first element as average of A1 and A3, which is going to be called as A1 star. Here A1 star is evaluated. A1 star is A1 plus A3 by 2, average of this A1 and A3, area of cross section at the point of application of the load A3. So, this average is coming around 700 mm square. In the finite element model, first element we are going to take area of cross section as A1 star. Similarly, when you come to the second part, in the second part we are going to take this area of cross section as average of A3 and A2. A3 and A2 average, this is A2 star, which is calculated 500 mm square. So, why we are doing this equivalent stepped bar model means, now you see the shaded region. The shaded region is minimized. By doing this model, finite element model, we can reduce the discretization error value. So, we can get the solution very close to the exact solution. When we do manual calculation, we can do this type of equivalent stepped bar. So, the tapered bar, which is given with variable cross section, is converted into an equivalent stepped bar. Suppose if you want to minimize this discretization error further, means what we have to do is, instead of the two element model, we can go with the multi element. So, more if you increase the number of elements, then if you adopt this concept, definitely we can minimize the discretization error. But here we are going to solve the problem manually. So, we are limiting ourselves to the two element model. This is the way we are minimizing the discretization model by making a given tapered bar into an equivalent stepped bar. Now, once you make tapered bar into a equivalent stepped bar, then we can make the finite element model easily. This is the finite element model for the given tapered bar. So, the tapered bar is converted into equivalent stepped bar. Now, this equivalent stepped bar is converted into a finite element model. For the first element, we have A1 star as the cross section. Second element, A2 star is the cross section. Here I am showing the element number and node number. Element 1 has node 1 and node 2. Element 2 has node 2 and node 3. The degrees of freedoms are U1, U2, U3. The forces acting on nodes are F1, F2, F3. Now, we can easily apply this thumb rule, which we have discussed in the last part. When you make the finite element model, always we have to check with these points. We have to introduce nodes wherever there is change in geometry, change in material property and a boundary point. then load application point. So we have to check with this one for all types of finite element model. We have to apply this rule. Here in the given tapered bar, fixed end should be denoted by one node. So node 1 is fixed end. Similarly, load acting point is in middle. So this load acting point is node number 2, and there is no change in material property. So boundary, this is the free end, we are going on node point 3. So fixed end and free end are boundary. Load acting point is there. So P point load P. So that is given node number 2. In this finite element model, all these points are satisfied. So we can proceed further. And in the finite element model, we have to define the boundary conditions also. At node 1, since it is a fixed end, U1 equal to 0. And F1, force acting at node 1, F1 is equal to R1 because this is the reaction force. The reaction force plus self weight, because in this problem self weight is also given. We have to consider the self weight of the bar. So R1 plus self weight I am showing here. How to calculate the self weight? Let us see. At node 2, U2 is an unknown displacement. U2 is unknown. We have to find out. F2 is force P plus the self weight. Then at node 3 we have U3, which is an unknown displacement. So F3 is only self weight, because at node 2 only we have the force acting, the external force P is acting. As we discussed earlier, the node 2 is a common node between the element 1 and the element 2. So the load acting at node 2 will be equally divided and given to element 1 and element 2 while writing the element characteristic equation. So after this problem going to be similar to the stepped bar problem. So first we have to formulate the element characteristic equation for the two element. We'll consider element 1. So this is element 1, node 2. The degrees of freedom is shown here, U1, U2. And when you write this characteristic equation, the area of cross section is A1 star. A1 star multiplied by EL. So here material property is same. So we are using the Young's modulus E, and the length of the element is also equal. So that is why A1 star E by L, 1 minus 1 minus 1 1. This is the stiffness matrix. U1 U2 are the nodal parameters. In the right hand side we have both the self weight, that is force matrix. We have self weight as well as the external load. So self weight gamma A1 star L, gamma A1 star L1 by 2, 1 1 plus F1 F2. Then we have to substitute all the given value. A1 star is calculated 700 mm square. Young's modulus E 2 into 10 power 5 meganewton per meter square is nothing but 1 meganewton per meter square is equal to 1 newton per mm square. That is why it is written as 2 into 10 to the power 5. Length of the element is 150 mm. Then the stiffness matrix multiplied by U1 U2 unknown parameter. Then we have to substitute the gamma. Gamma is weight density actually, but in the question only mass density is given. So we have to calculate this weight density multiplying this mass density which is given in the question. In this question, rho mass density is given 7800 kg per meter cube. If you multiply this rho with acceleration due to gravity g value 9.81 meter per second square, then we will get the weight density. But when you substitute this self weight, we are A1 star and VL1 are in mm. So this gamma, which is Newton per mm, after multiplying the g, we are converting the unit into Newton per mm cube. That is why we are getting this 10 power minus 5. So 7.6518 into 10 to the power minus 5. This is weight density Newton per mm cube. So we are multiplying area and length divided by 2. 1 1 plus R1 is the reaction force fixed end. F2, since it is a common node, we are dividing the load acting at node 2 as P by 2 for first element, and the remaining P by 2 will be given to the second element. So this is the element characteristic equation for element 1. Then we'll reduce this equation like this, taking 10 power 5 as common, then other values taken inside the matrix, 9.33 minus 9.33. So this 10 power 5 is considered as common term. The remaining, so the 700 into 2 divided by 150 is equal to 9.33, that is taken inside the matrix. Here the self weight value is, after multiplying this one, we'll get 4.017 Newton is the self weight 11 R1, and the total load P is 1 kilonewton. So 500 Newton is taken here. P by 2 is 500 Newton. When you add these two forces in the right hand side, you will get 4.017 plus R1, 500 plus this one, 504.017. So this is the first element characteristic equation. Similarly, we have to derive the element characteristic equation for the second element. This is the second element shown. Node 2 and node 3, U2, U3 are the degrees of freedom, F2, F3 are the forces. When you write the element characteristic equation for this element, A2 star E divided by L2, 1 minus 1 minus 1 1, U2 U3, which is equal to gamma A2 star L divided by 2, 1 1 plus F2 F3. Now substituting the values, A2 star 500 mm square, E Young's modulus 2 into 10 to the power 5, L2 is 150, U2 U3 are the displacement, and here gamma value 7.6518 into 10 to the power minus 5 Newton per mm cube, 500 is the A2 star and 150 divided by 2, and coming to the external part, F2 is P by 2 because common node, already P by 2 is considered for the first element equation, and F3 is 0 because it is free and no load is acting, so we are putting 0. Now reduce this equation, we have to keep 10 power 5 as the common term, the remaining term will be taken inside the matrix. Similarly, you have to reduce this one, so we will see. So 10 power 5, here you are getting 6.67 as the constant. Then similarly in the right hand side you are getting 2.869 is the self weight, and plus a 500 0. So add this value, this 2.6869 is taken as 2.87. When you add these two, 502.87, here 2.87, and the second characteristic equation is this one. This is for the second element. Now after deriving this element characteristic equation, we have to assemble these two element characteristic equation. So how to assemble it? The same procedure what we discussed in the previous part. Again I will repeat the procedure. For easy understanding purpose, the two equation 1 and 2, element characteristic equation 1 and element characteristic equation 2 is given here, and for assembly we are going to get a 3 by 3 stiffness matrix because total degree of freedom is 3. U1, U2, U3 are the total degree of freedom. So how to assemble this one? We have to use this number 1 2 1 2 is given as a node number, and for second equation 2 3 2 3. So here when you use 1 2 3, for first one 10 power 5 is common, we are taking out. Then 9.33 is taken here for 1 1 element 1 1 in the matrix, then minus 9.33, and 3 1 3 1 there is no combination, so we are putting 0 here. Similarly for second row, first element of matrix, we are using minus 9.33 as it is. Then this is the common node 2 2 element, so the 2 2 element is there in the equation 1 as well as equation 2. We have to add this two value 9.33 plus 6.67. when you add it, we are getting 16. Then 2 3 combination is there in the second equation, so minus 6.67 we are writing it. Then coming to the third row, first element 3 1 is 0, then this one third row second part minus 6.667 we are writing, and 3 3 element 3 3 is 6.67 we are writing. When you assemble this matrices, stiffness matrices correctly, then you will get the correct solution. Similarly you have to assemble the degree of freedom U1 U2 U3, and in the right hand side you have to assemble the forces also, forces acting at the common node. So here first node 4.017 plus R1 we are writing as it is, Then second node, we have a common node 504.017 plus 502.87 is given like this, 1006.887, then 2.87. So this is the global characteristic equation for the tapered bar problem. Now if you want to solve for the unknown, what are the unknown? Here u2 and u3 are the unknown displacement. u1 is 0 because of the fixed end. So after knowing this global characteristic equation, we have to apply the boundary condition. So how to apply boundary condition? So at node 1 we have u1 0 because of the fixed end. We can eliminate row 1 and column 1 in the matrices. Since u1 is 0, we can eliminate row 1 and column 1 corresponding u1 degree of freedom. So remaining will be 2 by 2 matrix. When you use this 2 by 2 matrix, u2, u3 can be evaluated. In the next step, we are going to solve this 2 by 2 matrix to find the values of u2 and u3. So this is 10 to the power 5. Then this 2 by 2 matrix 16 minus 6.67 minus 6.67. Then 6.67 u2, u3. In the right hand side, we have 1006.887 and 2.87. By using calculator, we can easily solve this equation. You will get u2, u3 as this value. So when you solve using the calculator, it is better to take this 10 power 5 to the right hand side. Otherwise, we have to divide this 10 power 5 4 times with this matrix element. If you take this 10 power 5 to the right hand side, we have to divide 2 times only. That is, for that reason this 10 power 5 is taken right hand side. After solving these equations using calculator, we can get u2 displacement as 1.0823 into 10 power minus 3 mm. u3 is 1.0866 into 10 power minus 3 mm. So very low value. So 10 power minus 3 mm, right? That is in the micron level. Why we are getting very low value means the load acting at this tapered bar is only 1000 Newton. For that load, we are getting only this much amount of deflection. Now, before proceeding further, why we are getting difference between u2 and u3 is minimum. Here you see u2 is 1.0823 into 10 power minus 3. u3 is 1.0866 into 10 power minus 3. That means the variation is only in the third decimal. After considering 10 power minus 3, third decimal. Why this much small variation means, if you see this tapered bar, the load is acting in the middle. Then the total load P is carried by this top portion. So that is why the disflection of the top portion is high. And when you come to the bottom portion, element 2 has only self-weight due to this portion, right? Only this self-weight causes this small variation in the deflection. We have to know how to interpret the solution, right? So why the variation is very small means the second element is subjected to only self-weight of the element. That is why we have very small deflection value, that we have to understand. After knowing the deflections u1, u2, u3, we can calculate the element stresses. First we are finding the strain epsilon 1. By definition, it is u2 minus u1 divided by L1. So u2, the displacement at node 2, u1 is displacement at node 1, u2 minus u1 divided by L1 will give us the strain 7.215 into 10 power minus 6. Then we will multiply the strain with this Young's modulus E, we will get the stress. Stress value is equal to E multiplied by epsilon 1, 2 into 10 to the power 5 into 7.215 into 10 power minus 6. Sigma 1 value we are getting 1.443 Newton per mm square. So 1 Newton per mm square is megapascal, we are writing here. Element 1 is subjected to 1.442 megapascal stress. Say positive value, that is tensile stress. So because this element in the taper rod, for this element 1, it is like a tensile load. So it is subjected to a tensile stress. Now coming to the element 2, first we are evaluating strain. Epsilon 2 is u3 minus u2 by L2 by definition. Substituting u3 value and u2 value divide by element length, we are getting the strain very small value 2.8667 into 10 power minus 8 like this. Then stress, to find the stress, we are multiplying the strain with the Young's modulus E. We are getting the stress value. sigma 2 5.7334 into 10 power minus 3 Newton per mm square. Very small value of stress. So when you write it, it is coming as 0.00573 megapascal tensile. Why tensile? Because the node 3 is not a fixed end, it is a free end. So that is why the element 2 also having the tensile stress, but that is the magnitude of the stress is very minimum, because element 2 is subjected to only the self weight. That is why we are getting very small value of the stress. Now after knowing the stress, we have to evaluate the support reaction. Next step, we are evaluating the reaction force. So how to evaluate the reaction force? As we discussed in the last part, we have to consider this global characteristic equation. When you take the first row of the global characteristic equation, multiply with the displacement, we will get this R1 value. By doing this, we can evaluate the reaction force. This is the first row taken from the global characteristic equation. Multiply by the U1, U2, U3. You will get the right hand side 4.017 self weight plus R1. Substitute U1, U2, U3 value 0. Then this is U2 value, U3 value, and multiply this one. You will get the R1 value as minus 2013.80 Newton. How to check this one? Sum of the reaction forces are equal and opposite to the total external force. Here the external force is 1000 Newton. What is this 13.8 Newton? This 13.8 Newton is nothing but the total self weight of the tapered bar. So how do you verify that one? Here you can easily check in the global characteristic equation. When you add this one, 1006.887 plus 2.887 and 4.017. So when you add these forces, it will be equal to this minus 1013, that is 1013.802. Here also we are getting the sum of the reaction force is equal and opposite to the total external force. By evaluating the reaction force, we are able to verify solution obtained by the finite element method. In this part, we have converted the tapered bar into equivalent stepped bar. Then we used the one dimensional element to solve this problem. Thank you for your passion listening.